What we need is a good philosophy of mathematics and geometry, a good theory of abstraction, how to form concepts, abstractions, ideas in geometry and other subjects. There are some bad ideas out there, some bad philosophies. Um, some are kind of inexcusable, like thinking that math is just symbol manipulation or just a formalism or it's a fiction. There's so many things that those don't answer, so many questions, so many things it contradicts, such a denial of obvious uses of reason and rationality and thought. I don't see much excuse in those. Um, I think some people really got to get stuck in a corner with rationalism and some stuff like that and really not even want to look for a way out. Think rationalism is like has to be the only way, but it's wrong. So there's to be fictionalism. So much obviously wrong about it though, inexcusable. Some stuff, like what Plato did at his time and so on, it's wrong, but for what they knew at the time, not so inexcusable as some of the other stuff, like nowadays. Um, at least Plato was trying to defend rationality and reason, and he valued it, and he was doing the best he could with what he knew. Um, although, Aristotle did a lot better. So, how much Plato actually could have done better? He could have done better more. You can see what Aristotle, who was around the same time, Aristotle was Plato's pupil. You can see what Aristotle did so much better. So, on the other hand, there's a little less excuse for Plato, but um, he was a genius, first one to come up with philosophy, even though a lot of people had been wise before. Um, and he did do some important work, though he was wrong on a lot of answers. But it's been difficult figuring out what to do. A lot of us can't figure out such a genius thing on our own because it takes going down below the depth of what we've already learned. You could talk about what's a point, what's a line, what's a triangle, how does topology work, why is it topology? A lot of us cannot get down below that because to do this, you have to have a good theory of concepts. A lot of us can use our thinking, of course, just like we can use our running and our heartbeats, and we can eat and digest. We can use reasoning, but we don't know how to use it well as some people do. I mean, really, really well, like masterfully. We can all use it, okay, and so on, but, or again, like figuring out how it actually works, that's a lot more difficult. There's not a lot of people who can do that. But thankfully, once some people have, we can learn from them and apply some of what they did to understanding math and geometry and mathematical abstractions. After Aristotle, Galileo, Newton, some other people, Darwin, and then more recently the objectivist theory of concepts, now we finally have a good epistemology and a theory of concepts and some good metaphysics that we can use to understand this stuff and figure it out. And we have an epistemology that lets us see how things are connected and related. Like fictionalism and some stuff, that is unintegrated with the rest of human knowledge and with science and so much of human practice and life. It's unintegrated and unintegratable. It's such a contradiction and nonsense that it cannot be integrated and connected to what we know about human reasoning and all that. The Platonic view also, but not as much. Kant, wrong. Plato, wrong. But as wrong as they are and as bad as they are, they're better than like fictionalism or something like that. At least there's something you can think about. At least they recognize like something about math. At least they're trying. But some things we need to be able to answer, and we got to work on these as we think about more about philosophy of math and geometry from a good rational perspective, objective perspective. We've got to know, what is math? What is it about? What is geometry about? What does geometry study? What are its methods? You know, the methods of psychology are different than the methods of geometry. The methods of statistical inference are different than the methods of geometry, and so on. Methods for understanding human fitness are different than the methods we use in geometry. So what are the methods of geometry? Why is it part of mathematics and not physics? How do we form concepts and abstractions in geometry? Because it's different than like physics. You know, we do things different in physics than in psychology. How does proof work in geometry? How do we prove things? How do we verify? What's the proof process? How do we learn geometry? You know, how do people think about and use geometry? Those are some of the questions. There's more. You know, so for example, like, why is geometry so useful and practical? That's something that's a fact that we have to explain. How are things discovered in geometry? 3 more. How does geometry relate to algebra and arithmetic? How does it relate to other fields of knowledge? How does it relate to epistemology? Those are some things we have to answer to have a good, proper, valid philosophy of geometry. Of course, I'm not going to discuss all that. I couldn't even do that at this point. There's so much more to understand and really think about in detail. It will take a while. That's one thing why to do some of this, you really got to get your hands dirty and not think, oh, we already know, you're overdoing it. You have to overdo it, as Newton did, or Galileo, or Marie Curie, or Darwin, or these other people, Michael Faraday, and so on, Maria Montessori. You've got to overdo things and really dig down into things and see that, yes, they are that deep if you're going to understand this. Otherwise, you will never get this. It's not something, oh, I already know that. For this, no. It's not, oh yeah, we already have the idea of a triangle and all that. Okay. If someone thinks that and they're satisfied and they think that's the answer, they don't understand what's happening. You have to be able to see the epistemology of it. How do we know what a triangle is? How do we get the concept? How does our mind work? What's the cognitive mechanism going on there to make that happen? That's what we need to see here. To get a good philosophy of math, which is important in so many other things. To get a philosophy of geometry, I mean. How do we form the abstractions? How does it relate to other fields? What are we really doing? So, you know, it's something only for people who are going to have the discipline and depth to dig into it, and the persistence, and so on like that. It's difficult, very, very difficult, as I say, to really see what underlies your concepts. Where the heck do we get this? Where does number come from? Where does a number line come from? How do you cognitively reverse engineer that? Kind of deconstruct it. And you can tell that it's difficult because no one has yet in history done it properly. It'd be nice if someone had. But some people are doing some good work, like Pat Corbini. I listened to some of her lectures and they're really, really good. Who else is out there in the world doing good work? I don't know. I don't know them all. But there should be other people out there, you know, doing some of this too. Of course. But abstraction in geometry. Okay, I think if we look at how we form concepts, look at other fields, see what happens, and apply that to math. Like, for example, quickly, to get concept of red. Red, we don't get the idea of red in contrast to someone running. It's not like, oh look, someone running and some of this, oh obviously red. Yeah, I get what red is. Or red, squirrel, dog, cat, skunk, rat. Oh, red, yeah. You know, they're totally different things. You can't get the concept of red in this context with these animals. Those are mammals. They have different features in common, different things going on in comparison and contrasting in context. Red, you know, you could have, we get maybe a patch of red, some reds, a patch of yellow, and some yellow, maybe some yellows. But let's just say red, yellow, green, blue. You got these things that are similar. And having these lets you see what to focus in on, as opposed to a red thing and something running, or something red and all these other animals. And if you got all these other animals and you got this red thing, you might think it's, you know, you focus on the animal aspect of it or whatever. But here, you can see, oh, when you're teaching a kid, let's say, a kid learning the colors, lay these out, maybe some more red, yellow, green, blue. Then they see, oh, we're talking about this kind of thing. We focus on this attribute with these similarities and these range of measurements. And people know nowadays, impossible to know a long time ago. Now we know that this, the color, is like how we experience like frequency or wavelength of light. You know, that's what it's like these certain measurements that we're experiencing in a certain way. So before, people would have thought these were qualities. Quality? Quantification? Huh? Nothing to do with each other. There are some things that are quantity and some that are quality. But now we know, oh, look, a lot of these things actually do have quantitative aspects. But we got this in contrast to these. Same kind of thing, different though. So we get the idea of red. This, like, range of measurements, because there'd be different shades and all that. Same thing with yellow, you know, lighter, darker, bigger patch, smaller patch. The size doesn't matter. The shade, these other characteristics. You see red versus yellow. So it says, you get these similarities in contrast to these other things in their, like, measurements. You know, like wavelength or frequency versus these others. And that comes up in forming concepts of other things too. Anger, justice, government, consciousness, other things like that. Speed, force, field, you know. But so with some of the basic things in geometry, if we have like point, line, plane, solid, you know, we start out the axiomatic thing. The thing we see is that there are solids in the world. We don't start with points. That's nonsensical. That's getting things backwards. In understanding the world, in developing our knowledge of shape and all that, three-dimensionality is the given. You don't develop it from points or lines or whatever. You analyze things to get that. That's, you know, the Platonic view, or the way it's like taught to us, kind of is like backwards. You don't get points and make lines and make planes and planes and make surfaces. Ludicrous. Because for one thing, it's impossible. A point is supposed to be something with no dimensions. A line is a direction. A plane's got 2 dimensions. You can't get something with no dimensions and put them together to make something that's a line. People have pointed that out, like Aristotle. It's ludicrous. Where do you even put them together? You know, they've got to have size and shape and stuff, because if there's no dimensions, how do you put something with no dimensions next to it? You can't. How do you put them in a line? How do you know if they're in a line if you don't have the line yet? You know? It's like circular reasoning. Oh, look, we get these things and make a line, and oh, therefore there's a line, only if you know what a line is. You know, there's like so many mistakes and fallacies and contradictions in it. A point is a location in space. Okay. So point, line, line, plane, you get the idea. You can't get some planes and put them together and make a solid when planes allegedly have no volume, you know? You can't get 3 dimensions out of 2. It doesn't make sense. So it's more like we have solids, we know they're a fact. Solids have planes, we know that's a fact. We see it. It's given in the evidence of the senses. It's given that that's how the world is. And we got to grasp that reasoning comes from the evidence of the senses. People have a problem with some of this because they want to reject the evidence of the senses. That's part of their premise and part of the mistake some people make. And that's a mistake back at the root of Western philosophy. We got to reject, for Plato, not for Aristotle, but Plato influenced a lot of things also, unfortunately. We reject the evidence of the senses. We got to have a starting point in pure reason. What is it going to be? So they got to make stuff up. That's the reason why some of the axioms in geometry are done the way they're done, not because it's advanced or scientific or rational or correct or logical, but because some people made the mistake of rejecting the evidence of the senses as valid. That's an important thing to know. We need to know philosophy, history, and so on to know why things are the way they are. So we know that it's not because it's the right way. It's not because it's the right way, it's because mistakes were made. We got solids, we got planes, we got lines, we got points. So, like with a point, if we take that, you can think of a point is where some lines meet, or maybe some planes. And you can get the idea of, like you put a dot on the board, bam, there's a point. We're doing some drawings, you got more advanced in your knowledge, you're starting to make geometry more into a science and do more with it. We draw, we use things, we name, we know we make points, and a point is a location with, every time we have a point, no matter where you've got 3 dimensions: depth, width, length. But the thing is, those things are irrelevant, or we abstract away from them in context of what we're doing. It's so negligible, we ignore them. That's the proper concept of this. That's how we can really apply our concepts to the world. Because that's what we do when we abstract to get the concept of point. Or, in some context, like for what we have, the Earth is not a point. It's this big, huge sphere. Sphere-like. But if you get to this universal perspective, the Earth would be a little nothingness. Its volume, its 3-dimensionality would be insignificant by comparison. It's negligible in compared to this, so it could be considered a point. It helps you see that a point is contextual. It's not some absolute thing with not 3 dimensions. It has 3 dimensions every time. They are just negligible in context of what we're talking about. Exactly like when you throw a rock and you're studying its projectile motion, it's in a small region. Air resistance and other stuff is there. It's just negligible. It's irrelevant to our analysis, and it's a waste of time to think about because it doesn't really affect our conclusion or results seriously. It's not a good, efficient use of our time to bother thinking about that. Similar here. We abstract away from certain things, but know that they are there. So that's what the idea of point is. And then, of course, with a line. A line has, every time, 3 dimensions also in the real world. But we abstract away from it, the essential thing we focus on is that it's got a certain direction. Even this, thicker here, thinner here, jiggles and all this, but it's how we think about it conceptually that we're focused on. How do we do that? How does that process work? How does abstraction and concept formation work in geometry? That's what we're trying to think about here. The logic and epistemology of it, not like what you do when you kind of basically learn it and just stuff as it happens. How do we do this? Again, as objectivist philosophy, I pointed out, and I don't know who else on earth has thought of that so far. I don't know everybody out there. But I think there's some guy I heard about recently. I haven't looked into his work. What, Swedish philosopher? Golden Force. I think he's doing some stuff on a similar view of concepts like this. From what I heard, I don't know, I haven't read his stuff, I haven't looked into it, but doing some stuff similar in artificial intelligence, something that would be vastly superior to the LLM model. I think he's thinking about how this range of measurements can come up into play in having a computer-like thing, having a computer thing that works more like human thought than LLMs do or ever could, using this measurement omission kind of thing, range of measurements and all that. But I don't know who else. But a line, you know, again, when you see different ones in context, in contrasting with certain things, you see that, you know, that, and that, and that. That, all these things. You got these things in contrast to some others, other shapes. What do they all have in common? That they go in a single direction. They have to have other things. To go in a direction, you have to have length. If you're at a point you cannot go in a direction, there is no direction gone. You've got to go in a certain direction. There's got to be some length. There's got to be direction. There's got to be three-dimensionality for our world. Or two-dimensionality if you're just abstracting away and working on that. But two dimensions is not fundamental. It's an abstraction from the real world. What we see, that is the given. Two dimensions is a more abstract viewpoint on that. So 3 dimensions is not more abstract. 2 dimensions is more abstract. 3 dimensions is stuff we have as the given. But here, there's different thicknesses. You can have different colors. All these other things that don't matter. But in terms of the line, you know, what you draw it with, the material it's made of, the color, some things like that are there, but you abstract away from those, and you see what's more relevant is the length, the thickness, and you abstract away from that and see it's the direction. You're always going in a single direction versus something like that, or a jagged line like that. And that's modern terminology anyway. It used to be people would consider this a line. Now they do line versus curve. But go back further. I gotta look into when this changed and all that. But from what I've seen so far, people would call this a line too. And I'm doing more modern terminology where you're talking about straight line, straight line, but still a line where you abstract away from the different dimensions and see what matters is just this kind of like more one-dimensional kind of thing, just this directionality that's going on, single direction, directionality here. That's how we get the concept of line. Point, line, and of course for plane, you got these different surfaces. And, you know, we don't have to represent it as a rectangle, but that's what happens sometimes. surfaces. Every surface has 3 dimensions also, you know, length, breadth, thickness. But the thing is, when we're working on some of this, like sand or a piece of paper, what do they all have in common? They all have in common their extension in like 2 dimensions. And we abstract away from that and know that for a plane, it's always got to have a certain length and a certain breadth. And then that's got to be the case, and the thickness is regarded as negligible. There has to be a length, there has to be a width. There always is a thickness, but we abstract away from that because we care only about the 2-dimensionality of it. Just like when we talk about floor space or carpet or something. You know, you buy a certain amount of square feet of carpet, you know that there's always a bunch of thickness, obviously. Or you got walls to paint. You know, how do we paint walls? You don't get some kind of like 2-dimensional stuff with no thickness and apply it to the wall. It's impossible. It's ludicrous. Everyone, you know, knows that never happens. What you do is get a volume and apply it to that. Because, you know, you're assuming, they say, if it can cover a certain amount of square feet, then it's a certain given amount of thickness that's kind of uniform. There's always got to be a certain amount of thickness, but it's the 2-dimensionality of it that we focus on. That helps you see how that comes to play, how that's legit. And, you know, we talk about square feet with other things like that. It's that aspect of something we focus on, knowing there's thickness, but the thickness we consider negligible. And then, just like with red, there are different shades of red. There must be some. With planes, there has to be some length and width. We know it can vary, smaller or bigger. And when we learn more abstract ideas in math, we see it can extend like from near nothingness all the way more and more and more to infinity. Infinity is not a thing, it's not a place. It's the idea that the extension could continue mathematically. There's no definite limit to it, as there is a definite limit to, let's say, how big or small a human could be, or how much water can go in a glass. It's like infinite, not finite. In that sense, you know, in contrast to like how big a person could be, how much water can be in a glass. That's what infinite really means, in my opinion. So that's how we get some of these ideas with the idea of measurement and mission, getting a concept. Again, seeing that these things are similar in contrast to other things. They have to have a length, just like red has to have a certain amount of measurement, certain wavelengths. It's within a certain range of wavelengths or certain shades. And then we have to have a certain length, and then we abstract away from certain things we don't consider relevant. Okay, the line. And of course, this gives us a better idea of how this stuff is applicable. And, you know, we get points more by seeing a particular location or analyzing a line, not by putting points together to make a line. So it's kind of reversed. Lines are of such a nature that you can divide them further and further down to a point. They are not made of points in that sense. You know, because again, points, you can't get stuff with no dimensions and put them together to make a single dimension. Ludicrous, contradictory, nonsensical. But you can get something with a direction and keep dividing it down and analyzing to find a point. Doing a limit or whatever. Or seeing where they come together in this location. You know, which of course has 3 dimensions, but we abstract away from that. We don't care. We think, what is just the location? That's the idea of point. As opposed to, like, as I say, to some of the silly definitions in textbooks. And then take some other things in geometry, some basics, before you get up into something that's way more complicated, like all this topological stuff, where still you're seeing how some things are similar in kind, in quantitative ways. That's what some topology is about. So let's say some of your basic shapes, we got some of these just drawn up here quick, but we can see by contrast that it didn't take a whole lot to learn. You have all this whole library of shapes in your experience anyway when you get to this. It's not like geometry has a, basic has a monopoly on it. It's given in perception lots of shapes. Then we start focusing on learning a few. Experience is full of information we bring into play when we're learning geometry. This is not the starting point. Reality is the starting point. We already know dog shape, squirrel shape, cat shape, fork shape, spoon shape, dinner plate shape, the shape of different people we know, houses and all this stuff. There's all these shapes we've seen and experienced already. Then we start to focus on these simple ones. So we got this background of information already. This is not the starting point. All of our experiences up to this point, that's our starting point. Then we can see, oh look, in that background and in this more limited one, this versus this, square, triangle, circle. It can be easy for people to figure something basic like that out as opposed to topology. Most everybody gets this, not as many people get topology. But we can see triangle, look, 1, 2, 3, square, 1, 2, 3, 4. Or you can see the difference. Even if you have more triangles, then with more, then you can start to see, oh yeah, what do these have in common versus these? Triangles. And this. And or squares. So then you can see the straight-sidedness, the three sides. So with triangle, we got this kind of shape where they have a location where they come together, and you got all these lines, straight lines. The length can vary, the thickness, the depth. So there's a whole range of measurements that we abstract away from, but the ones we focus on for a triangle are just these lengths and how, then it's given how many sides there are. So there's always three sides, the lengths can be different. And it's that similarity is what we retain to get the idea of triangle. It's not there's some perfect thing where there's things with no dimensions at all right here, and there are these things with only length right here, which couldn't even come together. If you got a point here and a line here, this thing with no dimensions, you cannot connect up with something with a dimension. Ludicrous, doesn't make sense. So, like the idea of a platonic triangle where you got no dimensions to this thing. You got this thing with like three sides, but how the hell do you know if they have three sides since it's like vanishing thickness and all these dimensions? And then you got these points that have like no dimension. And how do you get that, which has no dimensions, and like, except for the sides, and then this thing that's supposed to be perfect and connected to this? You know, like, if it's infinitely thin, how can you even see it? How can you compare it to these, which is some thickness? Like the platonic triangle, as I think other people in the past have said, I think there's probably been critiques like this, it just vanishes into nothingness. It doesn't make sense. Although, unfortunately, people like that would say, oh, therefore math doesn't make sense. But the problem was they didn't have a good view of concepts, as we know now, because of the work some philosophers have done. Thank goodness. I'd never figured this out on my own. It's genius. But that's more of what we mean when we think of a triangle. It's not that there is no thickness. We know that the thickness is negligible. It's, or like a platonic triangle can't really have any length, because if it had a particular length, it would be for that triangle, and how would it apply to any other? So it's another way it doesn't really exist. Like, is that a platonic triangle? Or is that? How big is it? You can't talk about the size of a platonic triangle because it doesn't have one. You know? And then if it doesn't have one, it doesn't exist. No size, nothing to see, nothing to think about, it ain't there. Whereas if you have a good theory of concepts, you know, oh, a triangle has to be of some size. But it can vary. And we know it's in context, nowadays, it's in context of being planar as opposed to spherical geometry or hyperbolic geometry, whatever. We think of things as being in 3 dimensions that are perpendicular and planar to each other alike. But that's how we get the idea of a triangle. That's what it is. It's an abstraction away from this stuff, not some platonic thing. And clearly, it's not a fiction. People who say math is a fiction, hello? That thing in reality is not a fiction. It's obviously right there. Or, if some geometry is a fiction, well, throw one of those little martial arts stars at yourself and see how much of a fiction that is. It's not a fiction. Or this stuff, you get a piece of board cut out of this and throw it at yourself. It's not a fiction. There are squares. Try to roll this versus this. This is going to be much easier because there are things like this in reality. It's not a fiction. It's not a fiction. It's not a platonic thing or whatever. Same thing with this as applies to that, or with this, with the platonic stuff. What size is a platonic triangle? It doesn't have one, because then it would be a single thing. So it vanishes into nothingness. What can it be? Whereas with a proper theory of concepts, you know that a circle is this curved line that's always the same distance from a center point, center location. Okay? Or you could say the line comes first, and any point on this line is going to be the same distance from here as any other point. Because again, we can't put things with no dimensions together to make a curved surface like that. We wouldn't even know where to go. If you don't have direction yet, you ain't going to get it from nothingness. And this comes first. So we see that with the circle, there's this uniformity here in distance between the line and the point. Anywhere on the line, it's going to be the same distance from the center. Doesn't matter how big or small it is, we abstract away from that. And this commonality is what makes it a circle. So that's how we'd apply a good theory of concepts to see this. And again, it's got depth, which we abstract away from. It's not relevant, because we're focusing on the plane aspect, the surface aspect of it. And clearly it's thicker here than thinner here, but we know it's still a circle. Because we know that, there must be some thickness, but we abstract away from it and just focus on the distance relationship there. So with a good theory of concepts, we see. And once we see we got that, again, just like with the triangle, if we have a good theory of concepts, we know, oh, look, yeah. My concept of circle comes from knowing that it's this kind of thing. And if I see that kind of thing, I know it's a circle. I'm not comparing it to some like Platonic ideal or a fiction. So this is a better idea about geometric abstraction. How do we form geometric ideas? And part of the thing here, it's implicit, but I haven't said, is that it's an identification of something in the world. We're not thinking of things only in our head. It's not turning away from the world, making stuff up in our head. It's not like Plato said or Immanuel Kant. We don't apply ideas to the world and pop, then they get some nature that we force them into. No. These things were here. You can see in nature already. Bees had hexagonal cells before humans were ever around, so on and so forth. There were certain rock formations, there were certain shapes before any human was ever around to see it, and so on. Math comes from our conceptualization of what's in the world. Then, because we're human, yes, we can apply these things to make certain shapes. But they were in the world in the first place. And then we got certain things from seeing how they can work with number. There might not be a 12-sided polygon, but we see that once we see how things work with triangle, square, pentagon, hexagon, and using that in combination with how numbers work, then we can see these ideas about, other shapes. Hexagon, heptagon, octagon, nonagon, decagon, and so on. But that's abstracting away from we know about the world, not imposing something on it. It's coming from continuing our knowledge of the world in context of numbers, which already also come from the world, with shape. You can have one person, two person, three person, four person, many people, and so on. Well, triangle, four-sided figure, five-sided, six-sided, seven-sided, eight-sided, nine-sided also, So that's an important part of this too. That we are conceptualizing reality. It's this integration of the two that gives rise to geometry, not some pure reason thing only. And some things like that, that basic idea of abstraction, measurement, omission, seeing how things are similar and different in contrast, seeing about context, those things, principles of logic and epistemology, are what we need to apply to geometry to see how it really works. How we form abstractions, how we think about geometry, how we learn it, how we discover new things in geometry. That'll help. Just like I say with the red. You have to have things that are similar to be able to get the right, to get the concept of red. Similar in kind. Again, red, yellow, green, blue. When you got some things like this, then you can focus on the correct aspect. All these things are similar in contrast to these, so we get the concept of red. We got similarity, difference, contrast, and a context. We identify these, form a concept, that's how we get concepts, how we form them. And the same process applies with geometry. But in some ways, it's a lot easier in geometry. It can be harder to see, more abstract, but easier in some ways because, especially at the beginning, because it's just shape and a certain number of sides. We do not need to know some things that are much more abstract, like how to differentiate governments, how to differentiate degrees of crime. Some things like that take a lot more experience and knowing about the nature of things than some geometry does. Because the geometry is about something more readily available to everyone. And that's why younger people can learn geometry and become really good at it, like math also, before they ever, or not. I mean, geometry versus math, like they're different things. But they can get good at geometry, math, math more broadly than geometry. Geometry is part of it, but much easier because of the nature of the thing than justice or advanced things, concepts in biology, because it's more simple. You focus on, let's say, the number of sides, the length, this length versus this length, regardless of what the kind of thing is, this length versus this length. That's easier for people to grasp than trying to figure out the nature of two things. And so, we can see geometry is part of math because a lot of the methods are mathematical, the same. Some of the differentiations are based on quantity. If you got we can figure certain properties of it, figure out what certain properties are based on the number of sides. If these are regular figures, all the sides are the same and the angles are the same. That's what regular means in geometry. If they're regular, we know 4 sides, 90-degree angles. 6 sides, we'd have what? They're all 120. If it's regular, all the angles are 120 degrees. So we can reason like that. It's more strictly quantitative. You're not so much using quantity to get something, but it's straight up quantitative. You can use math in physics, but it's not straight up quantitative. You can feel the strength of get 2 magnets, let's say north to north, you can feel the repulsion when you get them close together. You don't need to go to the math exactly to do that. It's good to use the math to see what's going on. In here, of course, you can see bigger angle versus smaller, but then, we get 4 sides, this angle, 6 sides, 120. That's the stuff we do. It's more quantitative like that versus figuring out the mechanical mechanism in physics or chemistry. Why do these chemicals combine? Why do you get water? Or why, under some circumstances, do you get this kind of chemical versus the other? Because their angles and all this stuff can affect the chemistry and all that. But this stuff more purely quantitative. So part of geometry. So we see there, we got some answers to some of the basic questions, some things that are important. We see what geometry is about. And we did a starting point, and then you can develop a lot more from there to get to the more abstract things in geometry. We see how it relates to epistemology and concept formation. We see how the way we form concepts is the same no matter what. And we apply the same thing in geometry. And then no wonder it's practical, because it's about the world in the first place. We are forming abstractions of things in the world that we need to know to get things done. That's why we form some of these concepts, because we want to know something about them. Otherwise, it's a waste of our time. We're in the world, we're trying to get things done. Someone wants to know what the boundary of their property is versus someone else's, how you mark off a bunch of properties to do an experiment, how thick the soil deposit is left after the Nile flooded and resided, things like that. There's a lot of things in the world that we're trying to figure out, and we're using geometry to understand things and to help us quantify and measure. So it's comes about from the practice of life and survival. So no wonder some of this is practical, because they were developed for practical purposes, for survival purposes. What kind of thing do we need to work the soil and grow some plants? What kind of thing do we need to cultivate and harvest deer and elk and cattle so we can eat? How do we maybe protect and enclose some of them in certain circumstances? What do we need to do? We got to build something. How do we build it? What do we need? How much? So, or with a building, how do we make a shelter? What kind of things fit together well? What kind don't? Can we get a bunch of things like this and put them together and make a good wall? No. We need things like this. Or if you're going to use some things like this, you got to fill in the gaps with, like, mud, or develop something called cement or whatever. So in building, shape is important. And then when you start to decorate things, shape's important. What are the shapes and colors inside a house? On some decoration, on some drawing, on how, like, the shape and color of food on a plate, a lot of practical situations are there where we're using and needing geometry in its mathematical aspects. Then we see, of course, when you look at chemistry and physics and other areas, we know shape is very important. So this helps us see better how we get the idea of shapes. It helps us see why it's so important. So having a good epistemology is important in this. When it's Platonic, if it's this silly idea of fictionalism, we don't get this. We're clueless. You can't figure it out. They have these unanswerable questions. Again, some of those viewpoints are unintegrated with everything we know, and they are unintegratable. They cannot be connected as a whole entire totality to everything else we know, as they should be if they were correct. And then, geometric proof. A lot of this stuff is to be developed more, of course, but some of that, I think, is already understood partially because people developed some ideas about proof a long time ago by arguing through practice. They developed ideas inductively and they brought that into geometry. So somehow that's done. Some of these people already imported into their deductive systems things people had got inductively. Immanuel Kant, Plato, they got some of what people had figured out through experience inductively about how reasoning works and imported it into their systems and called it their own. But it wasn't. So some stuff we have about how geometry is proven is already fine. We just need to see that the axioms of those systems are wrong. Their basic viewpoint is wrong. We don't have stuff made up in their head or ready-made concepts that are imposing order on the world. Again, we have these things are objective because they're an interaction between our mind and the world. The mind has certain rules it must follow to have correct knowledge. That's what we've shown. That's what deduction and argumentation has shown, and science. To get some knowledge that's true, we got to go through a certain step-by-step process. We can't just do whatever the hell we want. Consciousness isn't free. There are certain rules of consciousness, certain cognitive mechanisms we got to go through to get true knowledge. And so it's this interaction between the given causal things in the world and the given causal things in our mind that determine truth. Not made up stuff, not social, not whatever, but what's given. And the basic stuff comes from the world. Even if you don't understand some things about what goes on in the mind, people can still get important aspects and fundamentals of objectivity by saying that you have to conform to the facts. A lot of people know that. Even without knowing a lot about concept formation and all that, induction, abstraction, similarity, difference, measurement, emission, even without knowing all that, they still know to some extent what objectivity is. And then, again, once you see that, there are certain mental rules I got to follow, and then what all are those things? You start asking yourself, okay, some things are similar. What exactly is similarity? What exactly is a contrast? How do we form concepts? What's an induction? How do concepts relate to induction? How does induction relate to causality? How does similarity relate to characteristics? How does magnitude relate to attributes? Things like that. You can start to see, get these questions, get some answers, and then really start to understand what's going on. And we could think more about proof. A lot of stuff needs to be done in philosophy, math, philosophy, geometry, get things right. But as I say, because some stuff was already developed well inductively, and then brought, and then like imported into some of these other systems. I think some of it's right. We just need to get the correct framework, a good epistemology and metaphysics in place to back understand it properly, to see how people understood it in the first place, instead of Platonic deduction or something like that. Then we can see more maybe how, since we form concepts like this, form geometric abstractions like this, how does maybe like induction work in math? How do we get inductions? Instead of being dismissive of it, as some people are, and saying everything's a deduction. I think that's ludicrous. Because then you get these problems. It's like, well, if you start with these axioms and that's all you got, then, I don't know, like Gödel or whatever, you got these things that supposedly math is a closed system, when that's just a misunderstanding of math. That's not what it is. Once you grasp that math comes from our understanding of the world, then some of those problems about math, you see they disappear, they're irrelevant, they're a attack on a false view of what mathematics is, a false view of epistemology and abstraction. They're not an attack on real math, what it really is. It's like a straw man thing. It's an attack on a straw man, not the actual person. So I think this epistemology, the objectivist epistemology, clears up a lot of things. So we need to get geometry thought of in an updated Aristotelianism. Look at all the discoveries that have happened in epistemology since Aristotle, all of these things about induction and all that, and then apply those to some of the stuff that Aristotle did get right, then we're going to have a good proper theory of geometry. Then we can answer all the questions. Then we've got our understanding of geometry and math as it should be. We see geometry and math as an integrated whole with all our other knowledge, not something separate and distinct from it that seemingly confounds us with its practicality and all this other stuff. So geometry comes from our understanding of the world. It is not a fiction, it is not symbol manipulation, it is not formalism. We don't look at some Platonic objects. There's not some Kantian concepts like this already made up that we use to organize a undifferentiated flexive experience with no identity. No, things have identity, it's given in the world. Geometry is looking at things in the world and identifying them and logically processing them. It is not having some axioms in our heads that we deduce stuff from. It's having a reality full of information. A lot of it we don't even know yet. And that's trying to unravel that information, unravel it conceptually. The information is there, we want to unravel it. We use geometry to do one aspect of that, to unravel things about shape. It's basically, geometry is a branch of mathematics that studies shape in all its measurements and variety that we still have to discover. That's why it's like an open system, so to speak, not closed. It's not closed by the axioms of Plato or whatever. It's open by understanding of reality and whatever there is to understand. It's closed insofar as geometry is geometry, but it's integrated with everything else, and it's an identification of things in the world and whatever there is to discover, which is seemingly infinite. So the thing is, we need to get that, see that we are studying attributes of things. That's its real basis. Three-dimensionality, then we can see surfaces of things, lines of things, lines left by a moving object, and all this other stuff. We got to understand how we form abstractions, how we form concepts. We need to see the role of similarity. Not there anymore, I erased it. Sorry. Similarity, difference, contrast, context. Apply that all through mathematics, because that's how we really form concepts. And one thing about them is there are abstractions from abstractions. We can get pretty much very close to experiential level, circle, square. Some things come from abstraction. It's not like to get parabola, there's some kind of Platonic insight. We look directly without necessarily needing anything to see parabola. There must be precursors to it. It's not a fiction we make up, and you can make up this story regardless of anything else, or you can just use these symbols regardless of anything else to understand and know what a parabola is. Takes cognitive development, a step-by-step process before it. It's an abstraction that depends upon other abstractions. So it's this theory, we understand that better. How things fit in the hierarchy of knowledge, the fact that there is a hierarchy of knowledge as opposed to a fiction, some concept you apply in your head, you put an experience out of nowhere, or something you can just like get Platonic insight into. No, there's a definite causal process. Cause effect applies to the mind as well as the world. To have knowledge of this, like a higher level abstraction like parabola, it's an abstraction from abstractions, and you got to apply this causal process to get to that as well. So that's another aspect of this theory of concepts and this epistemology that's important, that other epistemologies do not have. And then that is the theory of concept formation and abstraction and epistemology we need to finally understand geometry and get it on a good basis, as I say. And then to see maybe how we do induction in geometry and take it and run with it. And this finally, as I say, a theory like this finally explains how our concepts apply to the world, where they come from in the world, and how they're so applicable to other branches of knowledge, and we get this integrated perspective.